Okay, this lesson is on similar polygons. So this unit we're starting is similarity, and we are going to look at varying shapes initially, and then we're going to move into triangles as we move throughout the unit. So first of all, we need to establish and understand what a similar polygon is. What does it mean? How do we figure out if polygons are similar? What is a polygon? All those words. There's a few language pieces in here that we have to make sense of. So first off, let's take a look at just the idea of what does similar mean? So typically when we think similar, we think, oh, they're gonna look the same. They're similar. Typically when I say, oh, these two dogs are similar, they might look like almost equal or look the same. Well, we can kind of take that same idea for any kind of shape that we're looking at if we're talking about a similar figure. So we basically are looking at whether or not two shapes basically have that same looking shape to it, but they might have different sizes. And typically, if you can kind of keep that, they will look the same. They just might be a smaller or larger version of themselves. So having said that, we can look at, let's look at these three logos. We look at these three logos and we look to see, okay, which ones have the same type of shape to them, okay? They all kind of look the same, but you got to look into the specifics a little bit more. Look very closely at them and look to see, I'm looking at this piece here. You see this kind of swoop of this airplane that comes through? It's got kind of a shallow swoop here. In this one, it looks like a deeper swoop happening. And then in this one, look, it's got that shallow swoop again. So by looking at these three, we can kind of identify that, oh, this logo and this logo might be considered more similar in shape than maybe this one and this one, or this one and this one, for the simple reason of we look at the swoop of this airplane as it passes through the logo. Now, when we typically look at things in math, we don't just look and kind of guess at it. We do want to take it a little bit and be a little bit more specific on, is it really truly similar, and what identifies shapes as being similar, not just by looking at it, but looking at it mathematically to find out the exact nature of whether or not things are similar. So when we do that, we want to start to establish some values and identify things, because what we start to see is if we can look at maybe our three shapes are what we've got here, A, B, and C. So when I start to look at these, I do a visual. I look to see, okay, which shapes kind of look the same. And right now when I look at this, well, A is a rectangle, C is a rectangle. They're both rectangles. B, to me, looking at this, looks like a square. So if I'm looking just visually at them to see, oh, I see a rectangle and a rectangle, okay, those are two similar shapes. They look the same. But now we want to get into the math side of it. Let's get into the specifics of, are they actually similar? Meaning, let's look at the side lengths. Let's look at those relationships between the side lengths. So this side length to this side length, this side length to this side length. We want to see if there is a relationship that happens there that maybe we can identify something or recognize something. So let's go through the process of, if I want to take and look at the rectangles A and B, so if I look at both of these shapes, and let's look at the length ratio. So length meaning I'm going to take this length here of rectangle A and a square, a rectangle that has both sides equal, or all sides equal, is considered a square. So I'd be taking this length, this 1.5. Well, ratio means it's a fraction. So I'm essentially going, oh, the length of A, side A is 2.8 over the length of B, which is 1.5. Now, if I take 2.8 divided by 1.5, I get something like 1.9. It comes out to 1.86. So I round it. So I could do the same thing for the ratio between the width of both of these and see what I get. So that means I'm taking 1.1 over 1.5, and I want to know, what does that work out to? 1.1 divided by 1.5, I get 0.73. Now, question is, are they similar rectangles? Well, these ratios that show up, they're different. So because there's a difference between those ratios, between the length ratio and the width ratio, these are not considered similar rectangles. So we can do the same thing. Let's compare the shape of A to the shape of C this time. Now we're going to take the length ratio. So let's take that 2.8, and we are going to divide it by the length over here, which is 3.5. Now, if I take 2.8 divided by 3.5, 2.8 divided by 3.5, I get 0.8. Okay, so then I do the width ratio. So the width again is at 1.1 to 1.7. And 1.1 divided by 1.7 gives me 0.65. 2.8 divided by 3.5. Okay, so again, I look at these two and I go, these aren't the same. They're not similar. So now let's go C to B. So C being a length of 3.5 to my length over here of 1.5, I find out that 3.5 divided by 1.5 gives me 2.3. And then if I do the same, I take my width ratio, so 1.7 over 1.5, and I find out that I get 1.7 divided by 1.5 gives me 1.1. So those aren't similar rectangles. So we get into the specifics. We want to make sure that when we want to identify whether or not something is similar, we are going to compare those length and width ratios, compare the side ratios with each other, and find out if they all have the same side ratios, then we know for sure that we are working with a similar rectangle. So let's try another one. Let's look at these two pictures. We've got figures that have the same shape but do not have the same size, and they are said to be similar. So we look at this one picture. We see that it's got a length measure of 10.3 centimeters by a width measure of 8.1 centimeters. And same thing over in the second picture, looks like the identical picture. Here we have 5.7 centimeters for a length along the bottom and 4.5 centimeters for a width along the side. These two pictures basically have the same shape. Okay, they're identified as the same shape, but they aren't the same size. We know that based on our measurements. But they're said to be similar figures. So if they're said to be similar figures, then what we should see in theory is if we take this length measurement with a ratio to this length measurement, so meaning if I take 10.3 divided by 5.7, and I figure out what I get there, so 10.3 divided by 5.7, I get 1.81. That's what I get as a decimal. Now, if I do the same thing with the width, because this was length, now if I do width, I take, and here I'm starting with the same. So since I started in this larger picture with the length, I'm going to do the same with the width. So if I take big one to the small one, and those corresponding, so I'm doing width to width, and I divide this out, so 8.1 divided by 4.5, I get a ratio of 1.8. So because these ratios are identical, these two pictures are what we call similar. So we can do that for any shape as we move forward. As long as I'm looking at corresponding sides, I want to ensure that I am using the same corresponding sides to compare to. Now, you'll see there's different ways to approach this to show those ratios. What we showed above with our picture is we took a corresponding side, so in this case, AB, that corresponding side corresponds to the length of that A prime, B prime. They're just little tick marks in here to indicate that we're using the second image for it. So I can also show it like this, and this is what we did with the dog picture up above. The other corresponding side that I could take is BC, so it should equal this ratio of this side to this side, B prime, C prime. This is typically where we're going to use that type of a ratio. Either one of these works, but kind of our brains kind of operate of always comparing one side to the side of another, this side to this side. So that's kind of, this is the idea that we used up in the dog picture up above. So a couple things happen when we look at similar figures. So if we look at these two particular triangles, and I label them as A, B, C, so A, B, C, I'm looking at the vertices of this particular triangle. And this second triangle is P, Q, S. Well, these are similar. They're telling us they're similar. And notice that the vertices, so this A corresponds with this P. This B will correspond with Q. C corresponds with S. So that's why when you start to see in the picture that these are the same kind of colors, shades of colors, you'll notice that they correspond to one another. Now the other piece, the reason that they correspond, look at their angle measures. Angle A is 60 degrees, angle P is 60 degrees. Angle B is 80, Q is 80. C is 35, S is 35. That is going to be really important moving forward when we talk about similar figures as well. So you got to really watch those angles that they start to correspond. So that when we start to look at this to figure out corresponding sides, I may look at from P to Q here, this side here that has that 60 degrees and that 80 degrees on the ends. Well, that side that corresponds in the other triangle is going to be AB. You've got this 60 and the 80 showing up there, okay? I can't take PQ and correspond it to BC because those aren't sharing the same two angles. So the other piece, when you start to look at the labeling, I can look at this and say, hey, AB corresponds to PQ. But I also know BC corresponds to QS. So you can start to look at the order in which the labels are written. As long as they're written in the same order, then you will start to see which pieces correspond to one another. So two things have to happen in order for polygons to be similar. Their corresponding sides must be in proportion, so they must have that same ratio, okay? So that's what we're looking at. They have to have that same ratio. And the second thing that needs to happen in a polygon for them to be similar is that their corresponding angles must be congruent, or what we call equal. So angles need to be equal, and those side lengths have to have the same ratio in order for them to be similar. So let's have a look at another example. So in this example, Debbie works for a magazine and is adjusting the dimensions of some images to fit into an article. She's not certain whether or not she has changed the length and the width by the same amount and wants to find out if she has to use the same ratio for each direction. So she wants to make sure essentially that these two pictures are similar so that she hasn't stretched it in length more than she has stretched it in width type of thing. She wants to keep it in proportion. So the original photo has dimensions of 4 centimeters by 2 centimeters. And the changed image changed it from 6 centimeters to 3 centimeters. So what we want to identify now is, well, if we want to make sure that these are similar polygons, we want to make sure that the angles, all the angles are the same, that they're congruent. And since we're dealing with a rectangle, we're dealing with all those 90-degree angles in the corners. So we know right off the bat, looking at it, yes, we have 90 degrees in each of the 4 corners of each of the pictures. So that holds true to the one piece of identifying whether or not polygons are similar. Now, the second thing that we have to do is, let's look at the ratio of the lengths. So if I'm looking at the ratio of the lengths here, so this is my length here. I want to know this length to this length. So doesn't matter which one I start with. So if I'm going to start with the smaller one, I'm going to say 4 to 6 in this instance. So I'm basically saying 4 centimeters in the smaller one to 6 centimeters in the larger one. Well, 4 divided by 6, that gives me 0.66. It repeats. So now they want to know what the ratio of the widths are. So again, I'm going to start in this smaller one, and I'm going to say that's 2 to larger one being 3. Well, 2 divided by 3 also gives me 0.6 repeating. So what we're starting to see is that we have the exact same ratios. So has the same ratio been used in both cases? You betcha. Are these 2 rectangles similar? These 2 rectangles are definitely similar, because these 2 ratios are the same and because all our angle measures are congruent. Okay, so let's look at the next one. Family built a home in Regina and designed a backyard garden. Looks like a trapezoid. So they've decided to use the same shape for a new, bigger garden. So they want to make they want to make it larger, but they want to make sure that the 2 gardens are similar in nature, similar shape. So basically they want to make sure that their new garden looks like that they have the same angles starting to pop up. What we know with a trapezoid, this is parallel to this, which makes this side and this side to be identical in length. And it also means that this 71 degrees, this is also 71 degrees. And we know that this side is 109 degrees. So those pieces, so coming over here, if I know that this is 71 degrees, then this is also 71 degrees. If I know this is 109, I also know that side is 109. This is in a trapezoid. So those are special characteristics that we know for sure are happening. So now we just want to know whether or not these 2 shapes are similar. So looking at our angle measures, we're hold true to that. We're okay that way. Now we have to start looking and comparing side relationships. So what you notice in here is we've got 3 different side relationships that we may have to account for, and we have to make sure that every single one of those ratios that we start to compare, they all have to be the same. So in this instance, I am taking this side, AB, corresponds to, so I'm dealing with the 2 71 degrees here, that corresponds to this side over here, EF. So I'm going to have to take AB over EF as a ratio. I'm also going to have to take, I'm looking at other side relationships that I can see. So if this is 10 meters, I know this side is 10 meters. So if I'm dealing with 71 to 109, that looks like I'm looking at A to D. So I can go A to D. That relates to, in this case, E to H, which I know that, right? This side here would be 15 meters as well. So that's the other side relationship that I have to account for. But I also have to account for, look at this bottom of this trapezoid. So I'm looking at DC. It relates to, look at 109, 109, 109, 109. So it relates to HG at the bottom. So I have to make sure that these side ratios, all three of these, equal the same value in order for these to be similar. So in this case, I'm looking at AB. AB is 13.6 divided by 20.4. So in that case, 13.6 divided by 20.4, and I'm getting 0.6 repeating. I do the same thing for AD. So AD is 10 to EH, which is 15, and 10 divided by 15, that's giving me 0.66. So that, again, those two sides, so far so good. We're seeing the same ratio. Let's do the last side. We've got 7.2 to 10.8. So 7.2 divided by 10.8, and I also get 0.6 repeating. So because all three of these are identical, I can look at these two gardens. The gardens, they are similar because these ratios are all equal. Okay, last example. We want to know if these two polygons are similar. Now, this looks a little different because we've got all of these little lines in here. And all these lines indicate is this single line says that this angle measure and this angle measure are equal. But it also means that these single lines also are equal to these ones over here. So all these single ones would have the same angle measures to them. And these double ones, just to keep them straight, all of these double angle measures all are meaning that they are equal or congruent angles. They are the same angle measure. These little side ticks just indicate if this is 12 over here, that means this side length is 12 over here. And the double tick marks means that this 4.8 here is the same as this double tick mark over here. So it's just some notations in there that we have to just watch for as we're doing this. So that becomes very critical because now we have to think about which sides correspond with what. Because I look at my angle measures and I think I'm okay there. These two are congruent with those two. These two are congruent with those two. So my angle measures are all the same. However, these shapes are just, they're flipped, right? They're rotated differently. So we just have to make sure that we pick the right corresponding sides to match up. So if I'm looking at 15, this piece up here, so if I'm looking at that piece, it's going to correspond not with this piece up here, because this is dealing with these two angle measures, the small one single tick. I'm going down here, this piece, because if I rotated it, you can even look at the shape, it's just been rotated. So I'm looking at really corresponding 15 to 6. So that's one that I want to see if it's what I'm going to get for a value. If I'm looking at the side, this side here being 12, it's going to correspond with these sides over here, which is 4.8. So I'm going to want to know what that looks like. And then the last one at the bottom here is 20, but that, because it's with the little tiny tick marks of the angles, it corresponds to this top one, which is 8. So now if I take 15 divided by 6, I get 2.5. If I take 12 divided by 4.8, I get 2.5. And if I get the 20 divided by the 8, I get 2.5. Because all of these equal 2.5, I know that these two polygons are similar. And that is your lesson on similar polygons. So now you can go ahead and work on some of the practice.